Okay, let's start our lecture number 8. Before I start, let me just announce that these lecture notes on the website has been those have been updated today. So if you have downloaded this lecture, this class notes, just replaced by the new one. Okay, there's some minor typos and errors that I have identified and corrected. Today's plan, we are going to, in summary, we are going to follow this plan here, the summary. We'll talk about orthogonal functions and expansion in general terms, because now we are going to solve Laplace's equations and also Poisson's equations indirectly. For the case when the potential function depends on more than one variable. So today we're going to explore solutions in the rectangular coordinate system and in the cylindrical system in 2 dimensions. So we're going to talk about orthogonal functions and expansions, then the technique used to solve problems in general, right? Then we're going to explore Laplace's equation, and I'm going to show how to derive product solutions in both the XYZ system and in the R-phi system for problems that have the potential is independent of the axial coordinate. And we're going to outline and show examples of Laplace's equations, the numerical solution of Laplace's equation. Just do something quicker here. Rewrote. References for today's classes. Today's class is well, we have our ebook on chapter 3. We talk about this subject, and also African chapter 9 treats the Sturm-Liouville theory of differential equations, and he talked about the specific conditions for specific differential equations to generate orthogonal functions. So this is an important source of reference if you want to look a little deeper into the subject. And also Jackson, sections 2.8 through 2.11. Well, let's start talking about the concept of orthogonality in function space. Function orthogonality in function space, we are assuming here that our domain is a real domain. In other words, the domain is the space coordinate, the 3D space and time. Okay, right now we don't have time into the formulation, but the domain is real. Okay, so the function orthogonality has a good resemblance with vector orthogonality. Things have same principles. They are related. When we certain differential equations Hermitian governed by Hermitian operators, they generate, besides eigenfunctions and eigenvalues, they generate normal modes or orthogonal sets, set of orthogonal functions I mean, most of the differential equations that govern a physical phenomenon, they end up in Hermitian operator, differential operators, such as Laplace equations, Helmholtz equations for the wave, for the propagation, for electromagnetic propagation, and Schrödinger's equations in quantum mechanics. Well, the technique that we are going to explore, we are going to factor out the function as a product of 3 single variable functions, and some of those will yield, besides their eigenvalues and eigenfunctions, they also will generate a set of orthogonal functions. Okay. In a similar way to the vector algebra in 3D space, we have bases, vector bases in 3 dimensions, right? We have versors that we use to decompose other vectors in 3D space. Those versors satisfy a condition like this, the orthogonality and normalization condition, in which the dot product between 2 versors being equal or not satisfy this relationship. This is the Kronecker delta, which is 1 if the indexes are equal and 0 if they are different. And we have also a cyclic property of the system, which is not important in the case of our present case, but I mean, that's another property. And I mean, why are those things used, those versors? They are used to decompose a vector, right? Like this. You can always decompose a vector in terms of orthogonal versors. And if they are normalized, this AI we have a very simple physical meaning, which is the projection of the vector in the direction defined by versor AI. So also we can make a dot product between vectors. We define that in the when we reviewed vector algebra, and we can also represent this by this bracket operator, which is very used in quantum mechanics. We are going to use here too. Also used in linear algebra. I mean, this bracket and cat symbols. So we have the bracket, which is like that. This concept here, we are talking about the 3D space. I mean, we decompose a vector as 3 orthogonal vectors. But we can do an abstract extension of this concept. This can be extended for not for 3, but for any dimensional abstract space. Okay. So we could as well decompose, we can imagine those versors mutually orthogonal in any dimensional space, right? In function space, we are going to define and going to see why is this the case. We are going to have our generic single variable xi. Okay, and the domain in principle is going to be enclosed between limits a and b, and xi is a real domain. So this variable xi is real. We are going to define the scalar product between functions f and g. Recall that, I mean, we are going to do a little more arbitrary definition. I mean, even though the domain is real, functions over this domain might be real or complex. For instance, when we deal with propagation, we more conveniently use complex exponentials to represent waves in the complex amplitude space of the fields. I mean, you use those phasor for fields, so you can retrieve the real functions after some operation on these fields. So we're going to make a definition that the scalar product between functions in functional space, by definition, is an integral in the domain between limits a and b of the first one conjugate, f conjugate, second one dxi, okay? So for real f and g, this conjugate is not important. So f scalar g equals to g scalar f. On the other hand, if the functions are complex, right, fg conjugate equals to gf, right? So if you just make a quick calculation here, if I do the conjugate of the integral, right, if I go here and do the conjugate, so we're going to have f times g conjugate, which is the definition of g scalar f. So that's what it is, right? So, I mean, in general, that's the property. Fg conjugate equals gf, just reverse the position. Orthogonal functions are those for which the scalar product is 0. And they can be generated either as a discrete or as a continuous set of functions. We're going to explore those situations. In general, they are, they can be generated. Most of the differential equations, they have an eigenvalue, right? But I mean, orthogonal functions can be generated as the solution of specific differential equations that fall in the category of Hermitian differential operators. We can intuitively try to understand what the dot product in functional space might represent, right? I mean, f dot g, right? Let's, for instance, just consider real functions. By definition, let's say that x is our domain. Let's say from a to b, right? fx, gx, dx. In fact, this is a measure on how, this integral gives a measure on how f resembles g, okay? So how f correlates to g. For instance, if I have something like this and something like this, well, they are similar, right? But I mean, if I have something like this with some property and something like that, we see that here we might have the possibility of having a small value integral in this case, because we have here a function that has a single lobe, right? And the other one has a double lobe. And you might cancel here with that contribution. So you might have different functions. So they might be orthogonal in that sense. One function has a behavior much different than the other one. I could not reproduce, in other words, I could not reproduce approximately this function here with this one there, right? It's very difficult to reproduce, right? You always have to have a negative part. We don't have a negative part in this one. On the other hand, I can approximate this function that's undulated by this one more regular here, a little, with some error, right? But it's easier to approximate. I mean, this one resembles that one a little more than in this case here. So we see that, I mean, orthogonality is a measure of resemblance. Things that resemble each other have some projection, you know. Things that do not, they are orthogonal in that sense. I mean, I cannot say that one function is a multiple, a constant times the other one in approximate form. Okay, so that's the concept of orthogonality. So we can also do some if I have a discrete set of orthogonal functions, let's say represented by a capital U over a discrete variable n, and it runs for, let's say, 1, 2, 3, and so forth. I can always normalize these functions so that the scalar product between functions in the set is always normalized. I mean, if we choose initially functions that are not normalized, I can always calculate the dot product, calculate that integral, right? Just go here, calculate un of xi times conjugate times of xi, dxi from a to b. So you calculate that, gives me a k n delta n, right? Which is this result here, right? I can do that, but I mean, to avoid having to make the same, to make it similar to the vector space, I'm going to normalize. I have versors in vector space. I'm going to have some normalized functions, in the sense that when I make the dot product, I mean the scalar product between orthogonal functions, if they are normalized, the scalar product is going to be unitary. So to do that, I simply define the normalized function divided by this factor here, root square, because when I do now, the scalar product is going to be a Kronecker delta also. So this is a very key, an important property for the decomposition of functions. I mean, orthogonal functions play the same role as versors in an n-dimensional abstract vector space. Okay. Suppose that, for instance, I want to decompose a function as a linear combination of orthogonal normalized functions, right? So what do we do here? I mean, is it possible to do this? Well, we just use the. It's the same thing that, I mean, if you want to answer the question, let's make an abstract n-dimensional space now, talking about vectors, right? So if I have a vector, I want to decompose on n in the mutually orthogonal vectors, right, versors, in n-dimensional space. Abstract space is not something that we see, it's not a 3D space. So what would we do? I mean, I would make a dot product with AM, which is one of the indices in the set. Okay, so I would do that. So I would have this result, right? And this is delta nm, and m is fixed, n is variable. This is going to be am. So the nth projection is the dot product of the vector with a basis vector or a versor am, right? That's the same concept. The spanning functions in orthogonal functions, we can apply the same concepts, right? What is this? I mean, suppose that I want to expand the function as a linear combination of orthogonal normalized functions u lowercase um. Then what I do, I just apply the scalar product. I pick one of the functions in the set, make a scalar product with the function, which in fact is to make this calculation here. Okay, so what happens? So formally, instead of doing all of this, just symbolically this operation here, and then we're gonna have the operation is linear, so I can apply this individually to each function in the set. So we're going to have a chronicle delta, and then we have an isolated element in the same fashion that we had in vector space. So the mth coefficient is simply the dot product of um and f, right? So this has a meaning. Why is this real? Why is this so, right? Let's see how we prove that. If you look at the root mean square error between for the approximation of a function by a linear combination of a finite set of orthogonal functions. Okay, let's look at that. We're going to see that this expansion is such that the root mean square, the RMS error, is minimum. Okay, so we say that the function converges to the linear combination in the average. Notice that you cannot use all the functions, have an infinite set of functions. You have to truncate somewhere, so we're going to have some error. So to do that, we just calculate this root mean square error representation, is proportional to it, which is the difference between the function and this expansion representation. So root mean means that we make that. After we calculate that, we can extract the square root, okay? And you have a number that you give it the percentage change error, right? So let's calculate that. Can expand, right? I'm just going to do it here separately. We're going to do f minus sum. Let me see, the index is n. N equals 1. I'm going to have a finite set of terms to make it calculable, right? an, un, I'm not going to put any arguments yet. So this is the conjugate times the term that is within the magnitude symbols. So there's going to be f conjugate minus an conjugate un conjugate. Same thing here, right? An here I have to be careful because I'm going to make products here. I'm going to put a different index here, okay? So you don't, when I make products of sum times sum, I have to put different indices because otherwise you're only going to pick terms of the same order, right? So here we have to make different indices so we don't lose information. So this is going to be f with f is magnitude of f squared. The other term is this one with that one. Sorry about that. This one is not conjugate. This is normal, right? So it's going to be minus a double sum here. Okay, I'm going to just put like this. AN conjugate AM UN conjugate UM, right? And this is the integrand, right? Then we have some f is minus f sum over n, right? And the other one is minus sum over m, f sum over m of am un. Then what do we do? We're going to integrate those things. We're going to have an integral of everything here, right? From a to b of this I. This is the error. And then I want to minimize the error. I mean, I want to choose the coefficients A1, A2, etc., so that the error is minimum. So what I want to do is, for a given AK, I want to make sure that the derivative equals to 0. Right? That's one necessary condition for minimization, right? So I have to pick the kth term in this expansion. So you see that the derivative relative to, I mean, this is independent of AK, okay? This one doesn't depend on AK, but depends on the conjugate of the elements of the coefficient, doesn't depend on AK, okay? This one has notice that before, in this case here, I think there's something wrong here. I'm sorry, I made the calculation wrong here. Let me see. There is a F conjugate. Here is F conjugate, okay? This is F conjugate. That's the only mistake, I think. So, I mean, the integral of this product here over from A to B equals to delta mn, right? So we're going to have, before doing the derivative, let me just write down what happens here, right? Just do the calculation. Let me pick up this thing here. Repeat it down here. So we can see it and see the results. Now, I can do the integral separately. Let me just remove this thing here. So this F squared. So I'm not going to integrate, but I mean, I'm going to do the integral here. So this is going to be this I, dxi, right? This one here is going to result, I'm going to raise it, after integration, right? So after integration, this term here gives a delta function, and m equals n. So this is going to be it's going to be sum in either index. Let's say m. Let's say n, right? N equals 1 to n. an conjugates, right? Then, well, so on the other terms, but this was only done for us to calculate the integral. Notice that this last term here is simply the dot product and this one too, right? Let me just write down those. This one here, after integration, right? This one here, after integration, is the this is minus sum. I mean this term here. This is the after integration is going to be an conjugate n scalar product with f, right? I'm just going to do it, and this one here is going to be sum minus, right? Sum n equals 1 to n. I can use again n as a dummy variable, an. So the conjugate of un, the property that we had before, right? Un scalar product f, because here we have the conjugates. Okay, so now we have the error function, which is this one here. So I want to make the derivative relative to kth variable. So the derivative, now I can erase it like this. I mean, the derivative of this is 0. Okay, the derivative of this is 0. The derivative of this relative to k is the coefficient of ak, which is this one. So this is going to give me one term only, minus ak. I'm sorry, this also is wrong sign here. This is plus. I'm sorry, plus. This was plus here, okay? Because it's minus with the minus. I forgot that, okay? So it's going to be plus ak. And the derivative of this term here is the kth term, which is equals to minus ak minus a derivative relative to ak is 1. So it's going to be I'm sorry. This is I forgot to put the conjugate, right? Again. Oh, this one here. Oh, sorry about that. This one has a conjugate here. I forgot. Okay. So, and also, I mean, the derivative relative to ak is going to be ak conjugate. And this one here is going to be minus derivative relative to ak is going to be ukf conjugate equals 0. So that's what the minimization gives for each coefficient. So ak conjugate equals to, I mean to minimize, right? uk scalar product f conjugate, and which is the same as ak equals to the scalar product of the kth function, u function with f. So it's proved that the necessary condition, let's say. We can calculate this, that this is a minimum, okay? But I'll leave that to you to calculate why is this a minimum. So that's extremum of the function, but it's also a minimum, okay? So that's the prescription. If you want to expand a function as a linear combination of orthogonal functions that are normalized, orthonormal functions, well, the projection is going to be the scalar product of the function with the basis function, okay? There are some interesting properties of A set of orthogonal functions is said to be complete. I mean, if you pick all the functions, we'll have a completeness condition. To derive the completeness condition, just notice that the function, once it's expanded as a linear combination of orthogonal functions, means that the coefficient is given by this expression. Then you can plug it. I mean, you can calculate. I mean, you can express this as an integral, right? So this is integral from a to b un conjugate of xi f xi d xi, right? So you can plug that back in the expansion, and we interchange the symbols of integral with sum. We're going to end up with this relationship f of xi equals to this coefficient here, which is the nth coefficient, times un. But notice, so it means that function equals to this function of two variables, xi and xi prime, integrated with the function itself to reproduce the same function, right? Well, we know that which function has this property. The function that has this property is the delta function. I mean, if I want to reproduce a function at a given point, xi, I simply make an integral of that function on a variable point xi prime with the delta function of xi prime minus x, minus xi. Then I reproduce the function. So it means that this function here has the same property as the one-dimensional Dirac delta function. So that's the completeness relation, okay? It means that if you pick all the functions, you are going to generate a delta function. If you pick an incomplete set, right? If you pick an incomplete set, finite set, okay, this is approximately equals to a delta function. It's only going to become a delta function if you complete the set. I mean, use all the functions. So it means that if you have a finite set, you're going to have an not perfect delta function. We're going to show an example of this at the end. I might show you that. I have an example here. I'm going to show you a couple of seconds. Also, so that means the completeness relation for a set of orthogonal functions, normalized, right? Everything is assumed that the functions are normalized. I can also interchange, right, those arguments like this. So xi minus xi prime minus xi have a conjugate of xi prime. If I interchange it, I'll have just change the, this one is going to be the one that receives the conjugate attribute. Let's see some specific examples of well-known orthogonal sets. One of them is the Fourier series with sine and cosine. If we use these functions like this, I mean, this is a normalization factor, right? And they have this specific argument with positive values of n, okay? So let's call those un. So they have an argument 2n pi x over a. So it means that at x equals a, you have sine of 2n pi, which is 0. So it's a node, right? X equals 0. This is 0. This is the first node. And we have a certain node at x equals a. But let's do, in this example, the domain is restricted to x from minus a over 2 to a over 2, which is similar. It's just a shift in the origin. So in x equals a over 2, you have n pi, which is also 0. The sine function is 0. So those boundaries of the domain, those limits of the domain, are the place where the UN has nodes. Nodes at the left boundary, on the right boundary. The other set of functions is the cosine function. Let's just talk about this one. It's similar to the sine, right? Same coefficients. 2n pi x over a. It doesn't have nodes in x equals 0 or a. Okay? But has plus or minus 1. And for n equals 0, this is equals 1, right? So we have also one element of the series, which is the element n equals 0. And V0 is going to be defined for normalization purposes as a constant, but given by this expression. Because, I mean, if we calculate V0 by this one, it's going to be root square of 2 over a. But we're going to use this one because of normalization. We're going to see in a second. So these are functions that have a fundamental period of a. I'm going to draw them here. That's the behavior of this function. I'm going to just draw the sine functions are those that have nodes, right? Sine function. Okay. For instance, where's my well? This is n equals 1. N equals 1 is this one. Right? So we have 3 nodes, right? One here, one there, and one there. So we have that one. Then you go to the next. I mean, if you, this is U1, right? So you go to U2 is this one here, which has 1, 2, 3, 4, 5, right? So you can look at the number of lobes on each half of the. Look at the lobes on each half of the domain, right? I mean, U1 has 1 lobe on the right side, and U2 has 2 lobes. Number of lobes on the half of the domains gives the number, the index of the function. Then you go to to V1, which is this one here. V1 is this function. Here has a, you know, they don't have nodes, they just like that. And V2 is this one. Sorry. You see that, I mean, just by looking at those, right? It's not possible to resemble. For instance, if I want to determine if there's a component of V1 in U1, it might be. I mean, you can notice that it's not possible, right? Because that's U1, U1 is this one, right? And V1, I mean, U1 is 0 in the origin, at the origin, right? On the other hand, V1 is maximum at the origin. Has, totally different. It doesn't have nodes on the boundaries of the domain, but U1 has. So, I mean, you see immediately that U1 and V1 are very different functions. I mean, they are similar, but, I mean, one cannot replace partially the other one, right? So that's indeed, right? I mean, these functions have orthogonality properties. The U functions, when you make the scalar product, have this property, delta. U and V, they always have 0 scalar product. And the way we did for V, they have this property here. This is a quick look, right? I mean, I can make this quickly. Let's make x, right? dx sine n pi x, I said 2, right? 2n pi x over a. Is that right? Yeah. Sine, let's say just one of them, m pi x over a. If these things are different, this is 2, right? This is going to be a combination of cosine of 2 m plus n pi x over a, right? I mean, this product is a combination of this plus cosine of 2 m minus n pi x over a. So this is from minus a over 2 to a over 2, right? When you do an integration, I mean, unless, if m equals n, in this case here, for m equals n equals to minus a over 2 of sine square, right? This is equals to 1 minus cosine 2 times 2n is 4n pi x over a over 2 integral from 0 to a dx. So in this case, let me move this to here. Let me just erase this thing here. I'll move it up. You see that integral of cosine. So I mean, this is going to be dx over 2. This is minus a over 2 to a over 2. So it's going to be half of the length of the interval. So it's going to be a divided by 2, and minus the sine function a divided by 8n pi sine 4n pi x over a, from minus a over 2 to a over 2. And we know it's going to be 0 because the sine function of multiple of pi equals 0. So this is going to give a over 2, right? Also here, so if m equals n, you have a result. If m different than n, we're going to have integral of a cosine function is a sine of integer times pi on the two boundaries, on the two limits, is going to be 0. So this is always going to be 0. So if the indices are different, integral 0, is equal, integral equals to a over 2. And because of normalization, this in front of the, a over 2, right, cancels or multiplied by this square equals to 1. So it's normalized, right? So these functions have this property, right? I mean, all you have to know now is that these orthogonality properties are satisfied. So if you want to expand a function as a set, as a combination of u and v, including u0, notice that this thing here means, sorry. This is a DC component, let's say, of the function, the average value, right? So in general, I can expand a function like this, has a constant component plus a variation, which is represented by these things here. So how do you calculate coefficients? Well, this in fact is the coefficient of V0, right? So we have V0 separated here. So if we make a scalar product with V0, so what we do, V0 scalar product with un equals 0, V0 with Vn, n equals to 1 and forward. So it's going to be 0. So V0 with F is going to be V0 times B0 scalar product. By definition, it's going to be this result here, right? Because V0 there's no A here. Sorry, let me see, what is this here? So let me do separate here because it's kind of confusing. So fx equals a b0 plus some infinity, right? I mean, I have to use all the functions. So an un plus, how did I call here? Bn times Vm. So to calculate the coefficient B0, I'm just make a dot product of V0 with F equals to V0 with B. V0 is 1 over root square of A, right? Integral from minus A over 2, what is the domain that I chose? Okay, minus A over 2 over A over 2 of B dx, which is going to be A over root square over A times, I'm sorry, B0, this is B0. So, so B0, A over root square over A of B0 equals to this thing here, which is the integral of V0, which is 1 over root square of A times fx dx, right? So B0 equals to, this cancels this 1 over A fx dx, So means that B0 is the average value of f, right? But you look that as an expansion, one of the orthogonal functions in the set is the constant function. So that's the result we got. It's correct, right? So the remaining terms can be calculated by the simple, projection, right? Like those. So these are the scalar product with the basis function or the expansion function, of the orthogonal function un with f. Bn is the scalar function, scalar product with f for the cosine term, right? Can also use, we're going to employ that in mostly in using wave propagation, plane waves, right? Plane wave decomposition. We can also use complex exponentials instead of using sine or cosine. So we can define those normalized functions. I mean, it's much easier to handle those complex exponentials. Now we can use n, including n equals 0 again, is a constant function, and you have those n plus or minus, positive or negative. Let's use an interval between 0 and 2 pi. So it's I mean, for n equals 1, this gives you a fundamental period of these functions. So again, if you calculate the properties of the scalar product of these functions, you're going to see that they are orthogonal. It's easy to calculate, right? I mean, if we calculate integral from 0 to 2 pi of each function is 1 over root square of 2 pi, right? Exponential of j mx conjugate times the other function j nx 1 over root square of 2 pi, right? If I do that, this is going to give me the x. If m is different than n, then I have integration of sinusoidal functions over a period, which is going to give 0, right? For m equals n, this cancels to 1. It's going to be 1 over 2 pi integral, which equals to 1, right? So that's the property, right? So these functions have unitary scalar product. So they are orthogonal. Completeness, I mean, that's an interesting completeness relation here. Okay, so that's that definition, right? I mean, delta of psi minus psi prime equals to sum in all the functions, right? Of un conjugate of psi un of psi prime, right? That's what it is. So if we use the exponential, this is going to be equals going to be like that. Exponential of minus j to in x. So that would be psi, right? I mean, I'm using xi equals to x, right? Sorry. And also let me forget the factor here. J n x 1 over root square of 2 pi, right? So this is gonna give me 1 over 2 pi exponential of j n. This is n prime, right? Minus j, or if you want, n prime. J n prime minus nx, right? That's what we get. Sorry. I just mixed up things here. This is x prime here. Sorry about that. So it's going to be j and x prime minus x. Okay? That's a little different. Let me see here. This is right. Functions I use was j and x. Yeah. X minus x prime. Let me see if my completeness relation. I mean, I mean, the order here is not important because the delta function is always an even function, so it doesn't matter which is, if it's x minus x prime or x prime minus x. But I mean, if I use the original definition, the correct result is this one. There's a small mistake in the class notes, but I mean, the result that we got here, right? I got the other way around, right? I got x prime here, minus x. But here we know that this sum, I mean, I can change the order of x and x prime. I'm going to have the same results, okay? So that's also true as in the class notes and the way I derived. Both forms are correct. We can also use these concepts to establish the relations between coefficients in Fourier expansion of functions. We have then instead of Fourier series, we have a Fourier integral. So it means that if our domain, our finite size domain, which is length a, right? If we start increasing it indefinitely, so we have an unlimited domain, then our discrete set of functions becomes a continuous set of functions. Continuous in the index variable, because the index variable for a discrete change of the index variable, we have a continuous dependence. It's going to become, I mean, the coefficient that appears in the argument of the functions changes by a very small amount if we change the discrete variable. So we see here, for instance, let's consider the Fourier expansion using complex exponentials. There's one possibility in the domain minus a over 2 over a, between minus a over 2 to a over 2. We have our basis, our orthogonal set, basically is the exponential function, right? So if you calculate the scalar product here, it's going to give, I mean, it's going to give an orthogonality condition, chronicle delta, right? I mean, for m equals n, this gives 1, so it's going to be 1 the result. For m different than n, this is the completeness condition, right? We just spoke about it. Well, let's now let the interval A becomes arbitrarily large. So we go to, as A becomes increasingly larger, okay, let's make it L, okay? A equals L, so L grows indefinitely. So one thing is the argument that we have in the functions. Let's look at those arguments. The argument is the factor, the exponential functions. They have 2 pi n x over a. These are the functions that we are constructing. Okay. So these arguments, we're going to call it k. Okay. So we're going to have functions that depend on this factor k, x. So these are the functions now. So 2 pi over a times n, I call k. If I change n by delta n equals 1, right, because this is a discrete variable, what's going to be the change in the argument? Well, it's going to be 2 pi over a delta n equals delta k. But delta n equals 1, so this is 2 pi over a. As a is very large, the step change in k is very small. So k changes continuously. Even though we have a discrete change in n, but the scale factor as a whole, 2 pi over a, is a factor, right? Which is small. So the factor k changes by a small amount. So if I have a sum, right, fx equals sum. So we have an. So I plug here 1 over root square of a exponential of j 2n pi x over a. Then we have some, so this is going to be replaced by exponential of jkx. And here, we see that this sum here, we see that, because 2 pi over a equals delta k, okay, so a, so I can put very, very funny here, a over 2 pi times delta k equals 1. I can put this one right here, just to identify what the sum is, right? I'm doing some just tricky things, but this is just to identify what goes inside of the sum. So fx is going to be like something like this. Sum in n, okay. Then we're going to have an, 1 over root square of a. Then I'm going to use 1 equals to this one, a over 2 pi delta k exponential of jkx, right? So as n changes by 1, this factor here, so this is going to be, let's move this to the next page here. So we're going to have here, the coefficient here is going to be sum an, right, times a over 2 pi, right, exponential of jkx dk, delta k, right? So we are summing terms that are like this with a coefficient. I mean, because n is related to k, I can call this a coefficient. There's a missing 2 pi here somewhere. This 2 pi, there's a 1 over root square of 2 pi here because we had 2 pi there, right? So we have here a coefficient that depends on k. So as we make a change in variables, this we call it a k. So, I mean, this sum becomes, in fact, an integral, right? 1 over root square of 2 pi integral from n equals to minus infinity to plus infinity. K goes from minus infinity to plus infinity. So it's going to be something like this. Okay. So dk, I'm going to just use the symbol, differential symbol traditional, ak exponential of jkx. So that's how we expanded the function when you have a very large interval. The sum becomes an integral, which is the Fourier integral that we well know, right? Coefficients can be calculated by this simple operation, right? So in this case, we know who un is, right? The un are those functions. Well, let me find them here. Where are they? 1 over, yeah. So if you calculate that, you have to calculate it. Un with f. Where is it? Yeah, I mean, the un, you can see here, it was defined like this thing here. Let me find it for you. Where are they? Un. I just want to find the coefficient here. Where is it? Well, it's down here. Okay, that's where un is. Okay, un is this thing here. It's 1 over root square of a. So we have to do that. We have to make explicitly the calculation. 1 over root square of a exponential of j kx. I already used the k here. So to calculate the coefficient an, this is going to be integral from minus, a over 2, which is in the limit of a too large, right? To a over 2. So you're going to have dx 1 over root square of a exponential of complex conjugate minus jkx f of x, right? So let's see what that is. So root square of a times an equals the integral from minus a over 2 to a over 2 of dx exponential minus jkx dx. Recall that this goes to infinity, right? This goes to minus infinity, right? And recall that by definition, you see that ak here equals to 1 over root square of 2 pi an times root square of ra. So this factor here is 2 pi root square times ak. Right? 2 pi, this is root square of 2 pi times ak, which is a coefficient, Fourier coefficient, Fourier transform effect, right? Minus infinity to plus infinity, dx exponential minus jkx dx then we have our AK, right? It's just a matter of putting things in the right side. AK equals to 1 over root square over 2 pi. So that's the Fourier transform of the function. This is the result, right? You see also that when you have a continuous set, completeness and orthogonality is similar. It's a similar relationship. You see that you have those relations. I leave for you to demonstrate. Okay, this is the standard completeness relation. As the limit as a goes to infinity, we make the same tricks we did before. We show this important relation here, right? The delta function expressed as an integral of this type. Okay. So that's a representation of the delta function using analytical functions, or standard functions, right? The expansion of the delta function in complex exponentials. If you want to see how this works, I mean, let's calculate the limit as a goes to infinity of the integral in a finite domain of this exponential jkx. So we just make x prime equals 0 here, just to make a simple calculation. This is easy to see. This is going to be the integral of the imaginary part is 0. This is a real function, right? So we're going to have cosine, which gives sine. So we have 8 times the ratio sine of the argument over the argument, which is the sinc function. And now we can see what happens as we increase a. This is the sinc function of ka over 2, right? As we increase the argument, the scale factor, this sinc starts to decrease. This width here starts to decrease. And because we are multiplied by a, I mean, the amplitude increases indefinitely, okay? So that's how sinc function, I mean, as k goes to, as a goes to a very large number, this thing gonna shrink until we have a a delta function. So only on the origin. The same concept can be applied for two-dimensional or for functions of two variables, right? This is just a formal procedure. So we have two domains. I mean, let's say that you are in a domain. I mean, functions over a domain defined by this variable xi and variable eta. Xi goes from a to b, so this is a and this is b, right? And eta goes from c to d. Sorry, BC and BD. So that's the domain for those variables xi and eta. So functions of those variables in this domain here. So we have functions of a single variable are orthogonal. Um of xi represents a normalized orthogonal set, and Vn of eta also represents a set. Let's say n equals 1, 2, etc., or from 0 and depends on the, let's enumerate from 1, but can be from 0 to 2. Okay, and those integers can be negative, so can be plus or minus 1. I mean, you see the example of the complex exponentials, that's how it was, right? So this function satisfies the orthogonality relations over the corresponding domains, right? So we can now construct the scalar product of the combination UV, VU, VU with VU. It's going to be, I mean, if those things are normalized, it's going to be something like this, right? So it means a double integral like that. That's a simple extension of the concept that we derived before. So it means that if I have a function of two variables, I can always expand it in these orthogonal functions, right? And obviously the coefficient of index Mn is going to simply be the scalar product of basis function, or one of the functions in the set, with f. So it's going to be simply like this. I mean, this prescription is very easy to extend to more than one dimension, right? So that's what we have. So that's what we have to say about orthogonality in function space. So now we're going to see how the Laplace equation generates orthogonal functions. Which of the differential equations that are resulting from the Laplace equations generate those orthogonal functions, right? So the technique that they're going to develop, I mean, they're going to describe, is called technique of separation of variables, also called, I mean, is also a way to generate a solution in the form of a product solution. The idea for a generic UVW system is to search for specific solutions that can be factored out as a product of single variable functions. I mean, for a generic solution of the potential for a problem in a system UVW, we search for solutions that has this property, that have this property, right? So why are we looking specifically for those special category of functions? Well, because they are going to be the seeds to obtain general solutions. So we start with those simple ones, right? That is this very specific property, and then we go to more complicated solutions, but we are going to use these base functions with these properties. If we do that, we can separate the differential equation in single variable differential equations. Some of those will give orthogonal functions, okay? So some of those equations will be Hermitian differential operators. They will be expressed in terms of Hermitian differential operators, and Hermitian differential operators always yield as solutions orthogonal set of functions. A set of orthogonal functions. So let's see in rectangular coordinates. I mean, I'm going to do in all the systems that we are exploiting in this course. Let's start with the rectangular coordinates. That's the simplest form of Laplacian in rectangular coordinates. Is the sum of the second derivatives applied to the function. Let's assume, for simplicity, that the function is a product of one-dimensional functions, like so. If we plug that into the differential equation, we see, for instance, second derivative relative to x, only x on f. Second derivative relative to y, only x on g, and so forth, right? So, for instance, the first term is going to give partial derivative, right? Partial derivative relative to x is going to be gh, total derivative of f x2. Same thing for the other ones. And for the last one, right? So we have this plus that plus this, right? Equals 0. What we do is to divide the terms by the product FGH. So we're going to end up with this first term is going to be like this after we divide, right? Second term is going to be like that. The third is going to be like that, and then we come to the most important argument of those separation techniques, is that this is a function of one variable only, if it is, it's only on x. On the other hand, this is only a function of g, and this is only a function of z, right? This or y, in fact, sorry, and this on z. So we are saying that we are summing three things: f of x plus g of y plus h of z equals 0, whatever x, y, and z in the domain, right? But I cannot have this equation balanced for any x, y, and z, because I don't even know who they are. I mean, who is f, g, and h? If I arbitrarily change those things. So the only possibility of balancing this equation is if I choose each term as a constant. That's the argument, right? This constant is called the separation constant in the problem. So let's assume that. So it means that I can always choose any constant I want. I mean, I didn't solve the problem yet, the specific physical problem yet. So I can use either real or complex constants, either positive real or negative real constants. I mean, each choice is going to generate a set of functions, which might work or might not work to solve the problem. So we're going to explore those situations, right? For instance, I can use one such a separation condition, a constant negative. Let's say all the constants are real, okay? So we're going to use a negative constant for the combination, which is this one here. I'm going to use 1 of f, 1 over f, second derivative equals to a constant, which I call minus alpha squared. And I do similar choices for the other combinations. That's the first one. So I choose a minus sign here. I choose a minus sign for g, for the g differential equation. But now, you notice that f of x plus g of y plus h of z equals 0. That's what I said, right? So f of x is minus alpha 2. G of y is minus beta 2, beta squared. So if those are real functions, I mean real constants, the only possibility for h is to have a plus gamma 2. so that gamma squared equals to alpha squared plus beta squared. With this choice, if these things are matched like this, I can balance the equation, right? So that's one possible choice. I mean, choosing two negative signs for f and g, and one positive sign for sign for h. So if we do that, the solution of those differential equations is very simple, right? This gives periodic functions as a function of x. This gives hyperbolic functions, exponential combination of two exponential functions, or hyperbolic sine and cosine, right? So for this choice of signs, we have f and g, a combination of sine and cosine. Alpha and beta are scale factors to be determined. We don't know what they are yet, okay? But you see that the oscillatory functions, sine and cosine, they have, I mean, we know that there are orthogonal functions that, depending on the domain, that resemble sine and cosine, right? And for the h function, if I can express in terms of hyperbolic functions, sine and cosine hyperbolic. So I have this set of choices, right? But in the same way, I can also use complex exponentials to represent the function. If my function were complex, right? If I was dealing with a complex function over a real domain, I would probably use complex exponentials. But I'm not doing that. I'm using potential functions, which are real functions, right? Laplace's equation so far is a potential function which has a meaning, a real meaning, which is energy. So I'm not going to use at the moment complex exponentials, but I'm going to certainly use in the future. And also, I mean, I can use complex exponentials for the oscillatory functions, and I can use real exponentials for the non-oscillatory parts of the solution, which are the hyperbolic parts, right? So you see that when I do that, I have several coefficients, right? A, B, C, D, and so this H is wrong, right? Just don't know what happened here. I just put D again. So you see, I mean, I already correct those notes, but keep finding those small mistakes. So you see that we have all these things that are unknown, but I mean, you solve that by applying boundary conditions on specific problems. Okay? So that's a general solution. Consider, for instance, the boundary value problem in the figure, in this figure here. We have a box. I want to solve the potential distribution inside of the box. And let's say that 5 walls of the box are grounded. The potential is 0, right? And all those surfaces, I mean, the xy, the wall that is in the bottom is grounded, and all the side walls are grounded, potentially, unless of a potential distribution which is imposed on the top surface here, right? Let's say that the function is an arbitrary function of variables x and y. So if we apply the boundary conditions, if we try to use one solution only, right, this combination here, we see that the solution which is going to have nodes at x equals 0 and a, y equals 0 and b is this solution here. Right? This part here has nodes in x equals 0, x equals a. This one has nodes y equals 0, y equals b. So I'm not going to have contribution of those cosine functions. Right? And also, if you look at the wall at at z equals 0, this wall here, down there, right, is grounded. So you have to have an hyperbolic sine function as dependence in z. So this one here is not going to be part of the problem, right? So you can show, you can calculate, you can apply the boundary condition and show that the solution that remains is this part here. Okay? Only the product of sine functions. Now, if we apply the boundary condition at x equals a and y equals b, okay, let's do that here. Let me use the candidate function phi equals a constant sine alpha x sine beta y hyperbolic sine gamma z, right? If I go to x equals 0, y equals 0 in those two walls, and z equals 0, the three walls, the potential is 0, right? If I go to x equals a, I have k sine alpha a sine beta y sine hyperbolic gamma z equals 0, whichever is the values of y in the interval 0b and z into interval 0c. So the only way to make to have the potential 0 for all these values here without making k equals 0 is to make sine alpha a equals 0. Then here we have a set of possibilities. It's enough that this be a multiple of pi, let's call m pi, right? So there's an infinite set of possibilities for alpha, which is an integer value times pi over a. M cannot be 0 because m equals 0 makes the whole thing, equals 0. So m equals 1, 2, 3, also negative values, but negative values replicate the same function. It's just a multiple of that function, right? So you see that alpha has a discrete set of possibilities, right? M pi over a. Same thing happens if you go to beta, right? If you go to beta, you're going to discover that beta has a specific form, which is n pi over b, right? M and n independent and positive values, and gamma has to be tied, right, to alpha and beta, like that. That's the condition. So we have an double infinite set of solutions for the problem of this form here. And here I'm calling those functions with the same representation, right? U functions of an argument, right? So that's applicable for x and that's applicable for y. What are those U functions? Well, the U function of xi equals to sine of mp xi. Okay? Those U functions have definite orthogonality properties, but they are not normalized. The way we did here, we didn't normalize it. But I mean, if you calculate the scalar product between two functions, right? Sine square is going to be 1/2 of the canonical delta instead of 1. If I put a root square of 2 in front of each one, then I would have normalized functions. But I'm not going to do that. It's not necessary. Okay? So the UM and UN are orthogonal functions in the domain 0 is smaller than xi is smaller than 1. And then I can use, xi as x equal over a or y over b. So if we translate that into integral over the x and y domains, we have those orthogonality properties, right, which are very similar. So you see that, I mean, we have now to satisfy the boundary condition on the top surface. But notice that on the top surface, the potential is arbitrary, right? And on the top surface, if we use this type of function here, it's not going to match the function at z equals constant equals c, because at z equals c, the function is very specific, it's sine times sine, right? But here is an arbitrary function. So what we have to do is, I mean, you know that one property that we didn't talk about is that if Laplacian of phi 1 equals 0, and if Laplacian of phi 2 equals 0, of course, because this is a linear operator, Laplacian of phi 1 plus phi 2 equals 0. So a solution phi 1, a solution of Laplace equation, as well as phi 2, the sum is also a solution of Laplace equation, right? So what do I do here? Well, if I didn't write down the solution here, sorry. So you see that we have, I'm going to write separate. We have solutions that I'm going to label phi mn, okay, which are a coefficient amn, scale factor times um of x over a, un of y over b, hyperbolic sine of gamma mn z, right? So we have an infinite set of solutions. So we're going to construct the sum and I'm going to force, sorry about that, all the possibilities, right? M and N. And I'm going to force that this sum matches the boundary condition at z equals c. So that's what you want, right? I mean, you want to make that at z equals c. I'm going to say that phi of x, y, c equals to the imposed function on the boundary, which is phi of xy. So it means that phi of xy equals to sum, the double sum, I'm going to just do like this, amn sine hyperbolic gamma mn c, which is the value of the coordinates, un, right? So you see here we have an expansion of a function of two variables in a set of orthogonal functions. So this coefficient here, right, can be determined by doing those functions are orthogonal in the interval between 0 and a. So what I'm going to do is to make the I'm going to put it like this because otherwise it gets confusing. Un of y over b, scalar product with phi. I'm going to put here xy. So if I do that, what happened? AMN, hyperbolic sine, gamma MNC. Immediately I'm going to have a Kronecker delta of delta. I'm not going to use it. I mean, I already used it. So the integral, this is going to be 1/2. The other integral is going to be 1/2. It's going to be 1/4, right? Sorry, but it's not 1/4. It's 1/4 is a over 2, because in the space it's going to be times a over 2 times b over 2. I mean, the integral here is going to be a over 2, the other is going to be b over 2. So we have the solution for the coefficient, right? So if we do the scalar product using orthogonality, we immediately determine the solution, right? These are the coefficients. So we solve the problem independently of the function that we force, that we impose on the top surface, okay? So these are the, the constants. So that's the solution. I mean, so you see that, I mean, this was a particular case in which the x and y dependencies were sinusoidal functions, periodic functions, and the z dependence was a hyperbolic function. Well, I could have made choices. X and z periodic and y hyperbolic, and so on, right? But it's always like this. It's always one hyperbolic and two periodic. It's always like that. Okay? That's what we have when we have 3D problems in rectangular coordinates. I mean, the eigenfunctions, the orthogonal set has always this property. If we had a 2D problem, we would also show that one of the components would be a periodic function, the other would be an hyperbolic function. Okay. For instance, I mean, sometimes it's more convenient to use exponential functions instead of hyperbolic functions, right? You notice that, just recalling that, the hyperbolic functions, right? They have, I mean, the hyperbolic cosines like this, and the sine is like this, right? They both grow indefinitely. They are unbound as x is very large. Sometimes if you have an open side domain, it might not be convenient to use. Instead of using those, you can use exponential functions. So I'm going to just show this example here. I have this semi-infinite potential well, in which the potential is grounded on two walls, has a finite value down, and as we go to very large arguments, the y coordinate, the potential goes to 0, right? So we have the boundary condition: potential at y equals 0, potential at x equals 0 and a is also 0, and potential goes to 0, potential at y equals to v, right? Sorry about that. And potential goes to 0 as y goes indefinitely. So in this case, it's more convenient to use a decreasing exponential for the solution in y, right? I could use the positive exponential, but the positive exponential goes to infinity, and the physical problem says that the potential goes to 0. So that component of the solution is not present. So the proposed solution is going to be something like, again, we have nodes x equals 0 and a. So we're going to have that sine function that has nodes on the extremes. In this case, the hyperbolic function was replaced by this decreasing exponential here. Okay, so it's very easy to solve the problem again, right? Just make the scalar product on each side and calculate at y equals 0. This term here, is going to be 1. And using the same prescription we just gave you before, I can calculate the coefficients. So the solution, I will leave for you to do the work this out. It's going to be something like this. M odd. Sometimes I find some word in Portuguese here. Odds. Right? So for y, very large y, for instance, we have an infinite sum here, right? But as y is very large, if you go very far away from the base, y equals 0, so this argument here becomes very small for any small change in y. For increasing values of m. So if you just keep the first term, could be a good representation of the potential distribution on a domain for after certain value of y in the region, right? The dependence. So the function has this. If we just retain the first term, that's the behavior of the function. Okay. I'm gonna give you some numerical results in a moment, but let's just see. It's important to notice that this solution that we obtain, right? It's right here. Has a closed form. This infinite sum. Most solutions in 2 dimensions for for surfaces that are regular surfaces, you can show by conformal transformation, which is a topic we are not going to talk in this course. But you can do complex mapping, a conform mapping, and solve lots of problems. Lots of problems governed by Laplace equations. Analytic functions, the real and imaginary parts of analytic functions, they satisfy Laplace equations. So that's why conformal mapping is something that works. So I'm not going to talk about it, but this solution has a closed form. Just look at the expansion. Forgot those things here. The expansion of the series expansion of power series Zm over m. Okay, and it can be shown that the potential is the imaginary part of this function here, this function with z given by this factor here. Okay. Well, let's see. Z equals to the exponential, right? Exponential of j pi x plus jy over a, which is exponential of minus pi y over a, exponential for j pi x over a. So imaginary part of z equals to, just to show you, minus pi y over a sine, right? Pi x over a, right? And also z to the mth power equals to exponential of minus j m pi, sorry, minus, this is times m, minus m pi y over, this is b, oh, is a, sorry, is a, over a, exponential of j m pi x over a. So the imaginary part of zm is sine of m pi x over a, right? So that's the idea here. So z to the mth power, and you see that z, I mean, is the sum of terms like this, which is exactly the expansion that we got here, right? We have sine right here, sine m pi x over a. Then we have an m here. Then we have 4v over pi, right? And we have exactly the factor that represents the imaginary part of this thing raised to the mth power. So if you look at the expansions of logarithmic function of 1 plus z and 1 minus z, you see that the indices are all indices, even and odd. Right? So if you change the sign, it's just a measure of adding a minus 1 to the m. So this is going to cancel that, and you're going to have a minus in front, which is the minus that's already there, okay? So if you now subtract those things, which is the same as making the logarithm of 1 plus z divided by 1 minus z, you are going to cancel the even terms, because even terms are similar. So if we subtract those, even terms are cancelled and odd terms are kept. But odd terms are minus 1 to the odd power, which is minus 1 times minus 1, which is plus. So the ratio is going to be sum over m odd only, and going to be a reinforcement of 2. So you see that the logarithm is 2 times zm over m. So it means that I can represent the potential, which is also an expansion like this, right? And we can have a closed form for the potential. So all we have to do is to do some calculation of the imaginary part of 1 plus z over 1 minus z, with z given by this thing here. Okay, let me just outline the calculation here for you people to do in the next. I mean, z equals to x plus jy, right? So let's calculate 1 plus z, let's call 1 plus z equals to let's call this r1 exponential of j theta 1. 1 minus z equals to r2 exponential j theta 2. So the ratio equals to r1 over r2 exponential of j theta 1 minus theta 2, right? So the logarithm of this, the natural logarithm, 1 plus z over 1 minus z, equals to the logarithm of r1 over r2 exponential, which is the product, right? It's the sum, logarithm of r1 over r2 plus j theta 1 minus theta 2. So imaginary part of the logarithm is theta 1 minus theta 2. So all we have to do is to find theta 1 and theta 2. So in fact, imaginary of log of 1 plus z over 1 minus z equals to theta 1 minus theta 2. So you can find it if we use z x plus jy, we have 1 plus x plus jy, right? Is the first number, and theta 1 here is the arctangent of y over 1 plus x, right? So that's how you have to do. 1 minus x minus jy, theta 2 equals tangent to the minus 1 of y over 1 minus x. Okay, so what we have to do is theta 1 minus theta 2, but let's calculate the tangent of theta 1 minus theta 2. We have tangent of theta 1 and tangent of theta 2 right here, right? Tangent of theta 1, tangent of theta 2 is y over 1 minus 1 plus x. Let's do that. And also tangent, this is tangent theta 1 minus tangent of theta 2 divided by 1 plus tangent theta 1 tangent theta 2. So, I mean, using these relations, you can calculate what you need, right? Because, let's see if it's right. Theta 1 equals 0, 0, yeah. Over 4. This is right. So we calculate the tangent, then you calculate the argument, right? Arctangent, right? But I mean, calculating the tangent is not going to be difficult because tangent of theta 1 is y over 1 plus x minus y over 1 minus x, right? Divided by 1 plus y over 1 plus x times y over 1 minus x. This is going to be y minus 2xy minus x divided by 1 minus x squared minus y squared. That's the result. Tangent, so theta 1 minus theta 2 equals to arctangent, minus arctangent of 2xy over 1 minus x squared minus y squared. And then we have to find the real part of x, the real part of z, right, which is x, and the imaginary part of z, which is y, with given z. So you can calculate that, okay? It's going to give the result showing in my showing here. So that's I'll leave that to you to find the final result, which is this one here. Okay. So just a quick comparison between results. We told you that for large y, just the first term is enough to approximate the solution. So see here, this is an example. This is, I mean, we calculate the exact closed form, right? Potential distribution as a function of x for a fixed y. So we have this exact result here. This is for the case y over a equals 0.5, which is not too large, right? You see that we have 1 to 2% maximum difference, which is right here, between the first term, which is the red one on the exact, and if you go to y over a even smaller, you don't have very bad discrepancy. You see, you have a maximum 10% difference between results. So just representing by the first term. Before we finish this part here, I'd like to talk to you about the special situation that we didn't explore for the case alpha equals beta equals gamma equals 0. So the separation constants are all equal to 0. In this case, you have equations that are like this, right? Equations that are like this, for instance, right? That's one of them. Solution is a linear function. Similar results for the other ones. And also for the other ones, right? G equals cy plus z, h equals 2d z plus e. So we have solutions like this. I mean, in fact, the solution for the potential is going to be, ax. Let's say, I'm going to put a prime, b prime, c prime, d prime. Sorry, this is e prime and f prime. So general solution is ax plus by plus cz plus then you have products, right? dxy you have eyz exz, right? F. And you have a triple product of three things here. x fyz and g xyz. So I have 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. There's one missing here. Plus a constant I forgot, plus h. So that's what we have. Let's see. Linear product of two things, xy, xv, yz, and product of 3 plus, yeah, that's what we have. That's the general solution, right? So for instance, hyperbolic surfaces in which the potential is constant, if we solve the problem in which if we have the, because I cannot show you here, but let's put in a two-dimensional here, right? We're going to make an intercept with the one surface, let's assume that we have something like this, the intercept. So we have a hyperbolic surface like that, right? In which the potential on the surface x, y, z equals 1, which is this curved surface, which is seen here in 3D space. Just saying that in this wall here too, this wall here the potential is 0, in that wall the potential is 0, right? And the lower wall, this potential is 0, and the potential is fixed at V in this hyperboloid surface. Okay? So in the region, which is the region between walls and the surface, okay, if we use this combination here, you see that you can drop the constant b, d, and e, and if you set the product a, times c times z equals to v, then you have the solution. So the solution on the form v, x, y, z satisfies all the boundary conditions. So the problem in this region here, which is between the flat walls and the hyperbolic surface, is given by this solution here. Okay? Which is one interesting case of solution of Laplace equation in which the separation constants are all equal to 0. Okay, let's go on. There's a class of problems which have a translation symmetry and in which the boundary surfaces are cylindrical. So in cylindrical coordinates, when we know a priori that the potential depends only on the radial and the azimuthal coordinates, okay, so what are the possible solutions that we can get? Well, let's try to find those product solutions and see what happens. If we expand the Laplacian in cylindrical coordinates, we have this, there's the radial part and the azimuthal part. We look for solutions which are of the form function of single variables. So we generate two differential equations after we do the separation procedure as we described before. And the azimuthal coordinate dependence is governed by the function g. For this choice of separation constant, I could use also a plus, right? I chose a specific sign in which here we have a minus, but I could have a plus there and a minus here, right? So we are going to explore in this lecture only one choice. So, but we have to pay attention to this, right? I have a different solution if I change the sign. So if we go to alpha equals 0, I mean, solution for G is easy, is a linear function. Solution for R is the same solution for the Laplace equation, in which the potential depends only on the R coordinates, because this is going to be 0, right? So here you have a log function plus constant. That's the solution of this problem. So the radial component is going to have a log function, and the azimuthal depends is going to have a linear function. Okay, that might be present or not depending on the problem. And for alpha different than 0, then we're going to have solution, periodic solution for G, right? You can write that in this form here. And for F, well, just assume we're going to explore that technique in the next lecture. Sometimes we use a Frobenius method, in which you assume either a single power of the variable, or a sum of power series of the variable. In this case, a single power of the function of the variable R is enough to calculate. I mean, look at the differential equation. Let me transpose it here. If I use this differential equation, and if I assume that F equals to R single R raised to the kth power, and if I calculate the derivatives, this is a separation constant. This is an unknown value that I want to determine. First derivative is k, k minus 1. Second derivative you see, if I plug this back here, I have r squared k minus 1 k minus 2 plus first derivative times r, which is k minus 1 minus alpha square k equals 0. Then you see that we have k minus 1 k minus 2 plus 2 plus k minus alpha square k equals 0, or k square minus k plus k minus alpha squared times r to the k equals 0. And for this to be 0, whatever value of r we have, it means that k square equals to alpha square, or k equals plus or minus alpha. Given alpha, the solution is a combination of two independent solutions, r to the alpha and r to the minus alpha. I have two solutions, two possible solutions, right? So the solution for the radial part in this case is something like this. Combination, right? So a general superposition of solutions would have the form log function times linear function of phi, combination of r powers, periodic function of phi. And we don't know what alpha is, so I'm making symbolically here a sum over the indices. Okay. There's some important remarks that we have to make here. The term, in the logarithm term, will arise every time that there's a line charge on the z-axis. A line charge, we know that line charge yields a logarithm solution, right? Also, we have to eliminate terms that diverge in the origin every time there is no singularity. So if you look at the solution, right, terms that diverge in the origin are this one and this one. So if the z-axis is included and there's no line charge in there or no singularity in the z-axis, so those constants have to be nulled, have to be zeroed. So we have to have that condition, right? Also, if the potential is finite for r large, for infinite r, we have also to eliminate the log component and the growing component, which is contained in A. And finally, if you have the whole domain phi between 0 and 2 pi, okay, then you have for the potential has to repeat the value every turn of when you go over the xy plane. So it means that you cannot have a linear variation in phi, because this increases by 2 pi every time you make a turn. So it means that potential will have more than multiple values at the same point. So it means that this constant has to be 0, 2. So these are considerations that have to be made when solving physical problems. Okay, it's very important to understand these considerations very well. So we have that property. And also the other consideration is that uniqueness of the potential, if you have the full domain, means that the periodic functions have to reproduce in every turn. Okay, so it means that if you have the whole domain, the whole phi variation allowed, this alpha has to be integer. So otherwise you cannot reproduce, right? Cannot reproduce the potential value. So I'm going to give you an example here, 2 examples there, right? Just, this is going to be on outline. I'm just going to go quickly through it, given the time that we are here. I want to show you an example, which is more important than going through these details, but you do that. For instance, the solution of this problem here, inside of the cylindrical region, right, with a given specification of the potential on the cylindrical surface, there's a problem that has no singularity on the z-axis, right? So no terms that give singularity will appear in the solution. We have only possibly a constant term plus a term that has a cosine function and cosine function here. These are sine of m phi, cosine of m phi. And inside we have, we have r raised to the mth power. If you are inside, if you are solving the problem inside, so the solution here is the smaller value is r over a to the mth power, right? That's what we have, which is the power of r, which has no singularity. So inside, we have the same solution, same coefficients we're going to determine, and the radial dependence is r over a. If you go outside, if you want to solve the problem outside of the cylinder, then the numerator is going to be a and the denominator is going to be r. So this symbol here, we're going to employ this in the course, in the remaining lectures, most of the time. R smaller and R larger are the lower or larger between R and A. That's the notation. So with that, we have a single representation of the solution, either inside or outside of the cylinder. Okay. So, and then we have those orthogonality relations that we have already showed you before, right? And we have those functions that satisfy those orthogonality relations, and you can easily determine the coefficients, okay? So, for instance, if you have two electrodes, V minus V, right? Like in this figure, in this picture here, potential is plus V on the top electrode, hemicylindrical, and minus V in the lower one. It's just a measure of applying the prescription, okay? So the solution is going to be of this type, and again, it has a closed form, and I will leave for you to do the calculations and calculate exactly this final result here, the closed form solution for this problem, okay? All right. Now, Laplace equation and all other differential equations can be solved numerically, and in Cartesian in rectangular coordinates is very simple, okay? And the other systems, we also find the numerical versions of the solutions. Suppose you want to solve the two-dimensional problem in which you give arbitrary values of the potential on the four walls. You want to find the solution in the middle. What we want to do is to make discretization of the Laplace equation. Let's see how it's done. We are going to approximate derivatives by differences, right? First derivative, we go, let's discretize x space in w long segments and the y space in h long segments. So derivative is difference, in fact, right? Fx plus half of the segments, which is delta x, minus x minus over w. Same thing, second derivative, if we do the same procedure, we're going to have this relation here. If we use that for y, for g, right? Same thing for g, we end up, if we apply, you see that we have a function and a function on the sides, right? So if we apply Laplacian of phi equals 0, we end up with a simple relation in which the potential at a given point is a sort of average of potential on neighbor points. Okay? If I make the increments, the discretization length equal on both dimensions, so this becomes a true average. It means that numerically, Laplace equation means that at any point the potential is the average of the potentials on the neighbor points. So we make a grid of points. At every grid point, the potential is the average of the potential on the remaining of the neighbor potentials. See? It's very simple. That's a simple way of solving the problem. Just open the last page here, which is taking some more time. So the idea of solving the problem is like this: we make. I mean, the idea is to pick the region and divide it into a grid of points, right? And the problem is this: I mean, what's the potential inside given the potential in the boundary? So you have the values of the potential in the boundary of your region, right? Those red points. So the algorithm to solve this numerically is to assume that the potential is 0 in the inner points, in the grid points inside, and you keep updating the potential in the inner points. Just start here, for instance. So here, calculate the potential as the average of this one plus this one, 0, right? Plus this one. Go to the next point, you update this one here, and you calculate the average on this point here. So you update all the values inside, then you repeat the process, and you establish that when the maximum magnitude of the maximum difference is smaller than a given value, you stop the iteration process. So it means that the potential distribution is going to establish in a way that all the points are consistent. I mean, one point has the average potential of these neighbors. That's how it's done. We have a pseudo algorithm here, just showing how to do it. Just initialize, these are the coordinates, discretized coordinates. You make a matrix in which you just in the boundary you define the values of the matrix, and this you put 0 values inside. So you're going to keep updating the inner core of the matrix, okay, using a for loop or a while loop, which is showing this pseudo code for you to take a look, okay? And also have an error function we initialize in a very large value here. And when the difference, we calculate the matrix, the new matrix and the old one, calculate the difference matrix and the maximum magnitude of this difference matrix. And we establish that the maximum change is not more than a certain percentage, right? So then you end the procedure, then you have the final solution. I'm going to show you two quick examples here. Just a second. I'm going to move the screen to my computer here. So I have hello, yes. Hi, yes, it's recording my full screen. Let me just pick my here. First, just how to plot those solutions. Solution of Laplace equation in Cartesian coordinates. Here we have, represents the solution the third axis, the surface plot, right? The third axis is the potential. In this example that I'm showing you, we have here the potential is a sinusoidal function on one segment and is zero in the other ones, right? I'm just showing here. That's the solution. It's just one term of the expansion, the solution, okay? You can calculate that. That's the type of solution is shown right here, right? This one here. Sine hyperbolic. So this is the solution of the problem of a sinusoidal variation, one lobe, right? One lobe here. Also, there's another problem here in which the potential is constant on one segment. I'm going to show you the Fourier solution. Okay, as we increase the number of terms, the potential is constant on one segment of the boundary. Okay, and we keep increasing the number of terms. That's how the potential resembles the combination of orthogonal functions resembles the constant potential. And in 3D space is something like this. Okay, potential is constant on one segment and zero in the other ones. So we have this ripple because as you put more and more terms, right? Put a lot of terms. Then we have that. You have an overshoot, which is Gibbs phenomenon, well known to Fourier, the composition Fourier series. You have those things at the edges, right? Now I show you numerical solution for, you see that the numerical solution for this problem in which the potential is given as constant on one segment and zero in the other ones. That's the one we solved in this lecture. We still don't have a nice behavior on the edges. But if you do a numerical solution, have a very nice result. Okay, this is one example in which this is the problem that makes you calculate numerically based on that pseudocode. This is done in Mathematica. Okay, so this is the result, numerically solved. So we have no overshooting, no rippling. So the solution is very well behaved. Okay, in this case the error parameter here is 0.04, so it's 4% approximately. Okay, that's the criterion I used in my code. So while error is allowed in 0.05, calculate, that's the same prescription I just gave you in my lecture. Okay, this is average of 4 potentials in the neighbor of the grid point ij. Okay, so you see that the numerical solution in fact is very fast. On the other hand, this Fourier transform, the Fourier solution, I have to truncate, right? If I put just one term, it's going to be the solution that we have before. Then we put more terms. Then we're going to start to resemble that solution there. Okay. So I think we had a lot, a very lengthy class today, lecture today, and we are going to conclude now, and hope to see you next time. Until then, bye-bye.